continue into more advanced topics tomorrow by presentation of Bogumi, when he's going to talk about random graphs of Julia and some more complicated applications. But the goal here was just to start totally with beginning, to talk slightly why Julia is useful for numerical computations, some very slight introduction to Julia, and then to discuss the graphs.gl library in Julia that is used for Julia manipulation. I have slightly too many materials for the times that is allocated, but I wanted, to put slightly more and just to use this all as a background material. And also everything is for download. So I've sent email. Hope you get them. If not, the tutorial for today and the tutorial for tomorrow by Bogumił is available at download. I'm skipping HTTP. Okay, so that's part of the address www.2023.zip. Okay, so this, if you want to download Szufel.pl, this is my name, /WAW, like the name of conference, 2023.zip. So these are all the files that I'm presenting. This was also sent by email. Okay, so this is what am I going to talk about. So let me start. So Julia is an open source language licensed under the terms of MIT license. Everybody can download it for free. And on this first slide, you have the address where to download. I will be working with Jupyter Notebook, like similarly you do in Python. You can also download Visual Studio Code, and then you have the EDA experience like any programming language. I'll be going slightly fast over some of the materials. So the language has very nice command line. It has package manager. It has several tools for managing the environment. You can install packages, and we'll be using some commands. So on my computer, I'll install some commands to install the packages required. For manipulation of graphs. Then what we are going to use, we'll be using Jupyter Notebook. And the Jupyter Notebook is a package named iJulia. So if somebody wants to start this Jupyter notebook, then you can do. Otherwise, in the zip, you have also HTML files. So I'm going to show source code. And if you just want to follow this code and do not want to install Jupyter Notebook for Julia and so on, then you can just navigate to HTML files. Okay, so it's all available for download together, Jupyter Notebook and HTML files, because sometimes it takes some time to install and so on. And I wanted to make it quick. So the goal about Julia is a language. This is a language for scientific computing. The idea is it's all summarized in one sentence, that it works like Python and runs like C. So this is a programming language that is a compiled programming language, supposed to be more useful than C, Fortran, or supposed to be more convenient than C or Fortran for numerical manipulation, and as fast as code in written in C, as fast as code in written in C for Fortran for scientific and mathematical computing. So there are many advantages to this technology, that maybe some of them we will manage to see. Just another side note: Julia can be compiled both on CPU and GPU. So a Julia program, of course, provided some conditions, because some things are not possible to be achieved on GPU, but a Julia program can be compiled both on CPU and GPU platform, which makes it more convenient. So if we look at the map of programming languages, here on one axis we have the execution time, and the other axis code speed, and the motivation behind why to create another programming language, because I'm somehow presenting something the less popular, was that either languages used to be have concise code like Python, but slow, or they had very long code like C, but were fast. And so, pardon? Yes, I can take questions during the talk, of course.
Just curious, how this performance for running time was estimated? So it was several classical problems to solve, or
Okay, so this one was for a specific use case. So this was some numerical simulation model. There are also benchmark across many. There are also benchmarks across many typical small use cases. Yeah, this is one specific, but there are also benchmarks. There are also benchmarks for other use cases. I'm using just only one here to explain, but basically across the benchmark for several use cases, the speed of Julia is more or less the same as speed of speed of C language. Bogomil wants to ask something about it. Yeah, sure. I can give you a microphone if you want to comment. Why not?
No, so just a short comment, because we are like, there are some mathematicians here. So it's a comment for mathematicians. So we talk about benchmarks, which is not like a mathematician would think, because it's not a proof, it's just an example. And of course, example can fail while the proof doesn't fail. The answer is you have those two dimensions. So for code length, we cannot give a proof, because it's like problem specific. So here you have to believe kind of that it's really a terse language. But for the runtime, in comparison to interpreted languages, it's like a proof that it will be faster, because interpreted language cannot be faster than compiled language, because Julia compiled to the same as C. So like on the low level, Julia will run at the same speed as C or Rust or whatever. Yeah, so you don't need benchmarks for this kind of, because it will be the case in general, not only in particular benchmarks. Whereas for code length, of course, it's the matter of the problem, because it's syntax.
Okay, so this looks like a good time to go to to this issue to this issue of benchmarking. So here I have Julia installed. Now I will be working, probably not surprisingly, with Jupyter Notebook, and as I guess this is perhaps the most convenient tool to show you how things are going. And so I will be of course using here and there some packages, like for example I have a package installed which is I have a package installed which is graphs and so on. Okay, so that's what so we'll see that in a minute. And now let us assume that we have a function. So we have a function written in the Julia programming language, function something, blah blah blah. Okay, so this is also an example of the syntax. And now what is interesting, it's that so I'm going to show slightly about this compilation issue. So about when this function like this is being programmed, it goes into multi-stage compilation process. So basically it's first being tokenized, then there are various compiler, and then machine code is being generated. It's also all can be controlled by something which is called metaprogramming, which is very nice for providing various mathematical abstraction for the language. Okay, and then I have, for example, so just a short thing. If I have a piece of code that is creating this function, so this is a piece of code. So first it's going to be parsed. So I can take this piece of code as something that has been parsed, and then, for example, I can use an abstract tree library to represent the code as tree. So a piece of code in Julia is a tree object. So the first graph here, I guess it's a tree. So a piece of code, abstract syntax tree of a piece of code in Julia is actually something that is manipulable by the language, and this is kind of first first stage of this. Then if I have a function like this, then it goes through many stages of compilation process, which I can observe. Normally we don't do when you program language, but this was by the question by the speed, and somehow, so I decide I'm not skipping this small example. So then we have this small function then goes to something which is called low-level virtual machine. So this is a set of compilers that is also available on macOS. So this is this code on LLVM already compiled. Normally you don't see such terrible things when programming, but here just for the example. And in the end, when you have this function, we end up having an assembly code. So this is just a compiled language like C or anything else. And you can poke into any compilation process. You normally don't do that, programs just work, but if you want, you can. And one more interesting thing, since you can poke into the any stage of compilation process, there are libraries like, for example, that can symbolically calculate derivatives of the code. So like when you need a derivative of a function, like you do some kind of optimization, say deep learning, and then you have plenty of derivatives to calculate, like you have the values of derivative to calculate the gradients and so on, and you do this many times. And instead of doing it numerically, in Julia compiler, in the compiler process, can actually create a symbolic representation of function derivative. So this code is fully mathematically manipulable, and there are many libraries that make full use of it. Okay, so this, why am I showing this, is that this code, or any piece of code in Julia is representable in Julia language, and it can be you can write Julia programs called macros that manipulate the code in the compilation process. Or for example, you have domain-specific languages, like there's a domain-specific language, say for mathematical optimization, like mathematical programming, and it's written in Julia using this macro system. And for example, in the compilation process, sometimes it can discover that variable is always 0, so you can kick out the variable from the model just by looking on the symbolic representation of some set of equations and so on. Okay, so this is how it goes. So this was maybe slightly too technical showing of the language. There's lots of materials on how to learn the language, and you have the links. In PowerPoint slides, and actually there is a great book written by Bogumił who is sitting there, and there is also a tutorial named Julia Express that can be downloaded, like the basic tutorial. If you know Python and want to quickly start up with the language, then clicking on this link is a good idea. Okay, so let us execute some basic comments. Okay, so you already see how to define a piece of code. So one thing, how we do define, so what we are going to need for graph manipulation, there will be some elements of linear algebra basically, and there are many other things in this tutorial for you just to browse, but I will probably focus on those related to linear algebra and that sort of thing. So how we can define a vector? So vectors are similarly defined as lists in Python. So for example, you can write 3x. Multiplication is optional, so you can simply write 3x. 4x, you could write in, but it's also okay to use mathematical symbols. Basically, Julia likes code using various things like LaTeX and so on. So if instead of x, I could want alpha, I can write /alpha and then tab, and then it's replacing this by a corresponding symbol. So basically, it's quite possible to have anything in Julia that looks quite like your paper, which is also the reason to use it for scientific computing. Okay, so we have here a list, so similar to Python. And another important thing about linear algebra is that all the lists, all the vectors and arrays use one-based indexing. So the first element of an array starts with 1, the second is 2, and so on. And it's like in mathematics, what we love, but it's not like in Python when it starts from 0 and then which is good for memory manipulation, but less convenient if you have equation that you need to paste. So there are many also nice tricks into how you make your code look more like paper. So if you have so for example, if I type /sum and do tab, I'm getting the symbol of sum, and I can say that symbol is equal to the summing operator. So I'm assigning the summing operator to that symbol, and then now I can use it. Okay, so this is the summing operator. So you can write also the stuff like this, and this is a proper code. It's still somehow similar to doing lists or enumerators in Python, because also in Python you can use rounded brackets, but it's very easy to get the code for mathematical manipulation that's like paper. You can also, for example, like here, use lowercase indexes. I can test. So how do we do? Like in LaTeX, _4. And tab, then I have v4 with lower index. So basically, some LaTeX symbol are supported via Unicode. Okay, so this is as it. This way we create an empty. So this way we create an empty vector. All vectors are type. So actually, as you can see here, it says, for example, vector float 64, and this is a difference from Python, and this is required from compiled languages, that each series of numbers need to have a definite type. So as you know, probably in case of Python performance for numerical computing, there are some projects that are trying to develop something called typed Python, which promises to great execution speed. There are tools like Numba and so on. So they try to make typed code. Also NumPy is typed. Like you have data types for matrices. In NumPy, probably everybody here knows NumPy. And the reason why NumPy code is so much faster than normal NumPy code is only because it's using types for its variables, and then it can be implemented in, say, C. You can also process complex numbers and so on. You have also like you might expect with any modern language, you have also support for rational numbers. So you can define a rational number like half plus 1/4, and this is 3/4, and then we can check the type of this is rational numbers. So actually, if I then go to the zoo of numeric types, then basically we have numeric types. Then we have real numbers. Out of that, we have integer. So these are the abstract types here. These are the abstract types, and below are concrete types. And now there is something which is quite interesting, and it's also again useful when computations. Some types have defined the space of numbers they use. So here we have a rational number, and rational numbers can be defined over a space of, say, int 8 or int 128 or unsigned int numbers and so on. So if you have a rational number, so one divided by the other, okay, so you can define what type you want to have. The same about complex numbers. So complex number can be defined over any real number space. So in this way you can combine types. This is called parametric types. Similarly, when we had here a vector, as you know, this is also a parameter. So this is also called a parametric type. So this is a vector of element float 64. Okay, so in this way, in this way, we have parametric types. So for example, if I have a complex number like here, I've defined a complex 1,4, then I can see this is a complex number defined over int 64. And if I do a dump over, so dump is show the internal data structure. So whatever is inside the object. So sometimes we want to see what is holding there. If I do something like dump this object, I can see that this is an int. This is an int consisting. This is an int consisting of 2 parts. Okay, so this is So this is like it. So this is like it works. Then we have. Yep. Okay. So abstract types are being used to define the type hierarchy, like here. So they do not. So you cannot create an object of number, but if you, for example, let me. Oh, I can do it here. A new cell. So number is an abstract type, so you cannot have something being a number type. Okay, but for example, if I can say that int, this is an operator, is a subtype. So int, an integer, is a subtype of random number. And sometimes you might want, for example, to do a function that is accepting something that is number. So let me say function, call it @5, and it take a, which is a number, and it's going to return a plus 5. Okay, so now what is going to happen? This function will not work with string, but will work with any number. So I'm saying, hey, I want any number. And then, depending on what I'm going to provide this function, I should be already to see here. If I'm going to provide to this function @5 int, I'm getting some piece of code. It's part of compilation. I wanted to show somewhere in the middle of compilation process. So it will be using the plus sign that is designed for int, and it will, in the end, compile to appropriate assembly code. And if I run the same piece with float here, it will compile it differently, because then it's going to use plus operator for floats. And what is this mechanism is called? Why the reason the answer is so long? It's Julia is using multiple dispatch. So depending on the data types, those data types are quite complex and quite detailed. It's changing the compilation chain, and you get very optimized assembly code, but the compiler just must know what are the types. So if you write a code in this way, we have like mathematical operations. So if we got two integers, we always know what we get as the result. Then if we have full information about types, that it can very properly generate assembly code looking at the types.
Again, with not pointer,
5? Yeah. So it's a different. Of course, I could go like to the. Okay, the complex. Okay, let's see. Okay, so complex 4 and 5. Yeah, so this is, of course, it's much more open, but then you get different code. Of course, this is in middle of the compilation process. Like I said, it has like many stages, but this is what is going to the low level, because it's an intermediate code for the low level virtual machine, and there is the final compilation stage. And as you know, all now popular languages like Rust, Go, and several others are now nowadays using low-level virtual machines. So this is the compiler hit for many modern programming languages. Yep. Oh yeah. Okay. Okay. So we have number pi. Okay. And this is number pi, and when we talk about type of pi, okay, so this is the type is irrational. So this is irrational number. It's a type of pi, and now what's going to happen? You can write the code, but at some point it's needed to be materialized. So it's going to be a pi as long as you do not do anything about it, but at some point of time we want to materialize it, and you could materialize it by typing a big pi, then you have materialization, and then you have something like set precision, because when you do materialization of this irrational number, you can say what big precision you want to have. So if I do set precision 20,000, then you have it like this. Okay, so if you've been ever thinking how to find the number of pi with some number of numbers, the shortest code is in Julia, as you can see, because there is this number. At the same you have with Euler numbers and other stuff.
So it's got a list.
Pardon?
So it's got a list of certain irrational.
Yes, it got a list of certain irrational, like all irrational numbers you are using. It has the list. Yeah, but you understand something?
Like not a list, because as you can see, you can define your irrational numbers as long as you can provide a formula for materialization when it's requested.
Okay, fair enough.
Oh yeah, this is a good point. And also you can also define your very own numeric types. If you are seeing here like int 128, there are libraries that provide int 256, 1024, and so on, and it's all natively compiled and it's all natively supported. So actually, you can all write your own providers of native other data types. And their mathematics is going to get properly translated into optimized assembly code. So it's really cool if you write this sort of thing. So I think. So this is irrational. What's a big pi? Okay, so this is a good question. What's this? You're asking funny questions. I mean, funny in the sense, funny to answer them. Okay, so it's a big float. So this is a special type that, because you need to materialize, and of course you don't want to materialize something like this to float 64 because it wouldn't make sense. So of course you can parse numbers, blah 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 blah. So there is something like at show to show something at the console together. So it says int from A, then it's like in any programming language. So this is something you can expect in any. This is something you can expect in any programming language. So you have tuples, and tuples work like in Python basically. Again, they are strongly typed, so everything has type in Julia. So many things work very similar to Python, but everything has very strong type information. Okay, and then we have matrices. So basically, if I write something like 0 int 2 3 4, the comments for matrices are going to work very similar to what you are seeing in NumPy. Okay, with the major difference that everything is numerated starting from 1, because NumPy, in NumPy and or in C++, everything starts from 0, and in the Julia programming language, everything starts from 1. Actually, a matrix, when you look type for representing matrices, it's an alias for a 2-dimensional array, because you can have 3, 4, 5, and whatever dimensional arrays. 1-dimensional arrays are called vectors. 2-dimensional, they have aliases in the language. Okay, as you might expect. You have array slicing operator. So if I have a matrix big like this and I want to select all the rows and third column, again, it's pretty similar. There are some small differences, but quite similar to what you could do in NumPy. So you can provide the ranges, you can provide colon to finish and start a range. Sorry for going that quickly, but this is just very quick. This is just a very quick introduction. Then you have other things I'm not going to present, like you can define your data structure. So Julia is not object oriented, but it's based on a type dispatch. You have dictionaries. You have dictionaries that work quite similar to Python. So this is a Python example, this is a Python example of a dictionary, and Julia defined them as a dict, but they work more or less like in Python. You have, of course, functions for text processing. One which is nice, which is text interpolation. You have examples here in the code. What else do we need? You have all standard mathematical operators, but there is one very interesting thing. In NumPy, when you do something, it's always working, it's always vectorizing the code. So if you are performing operation, it's always assumed that if, for example, if you are comparing two vectors, all elements of vectors are going to be compared. On the other hand, in Julia, if I have something like 1 to, if I have say 1 to 3, this is a horizontal one-dimensional matrix, or you could say it's horizontal vectors, because Julia normally vectors are vertical like in mathematics. And I want to compare this to 2, 3, 4. Then basically this is not going to work, because the comparison if operator is defined for scalars, not for vectors, and it's not automatically vectorizing the code. So in Julia, when you have operations, linear algebra operations, and you want to vectorize it, you need to explicitly say, I want to vectorize something, and you do not need to write a loop like in C++, you just add dot. So dot, it means you want to iterate over all elements of each of these vectors, and then we are getting here like bit matrix, so with Boolean values. Okay, so the point is that dot in Julia has very special meaning. It can be added into any your own function. It's all automatic, so you can add it to your own function. You can also define in Julia your own mathematical operators, and they will automatically work with dot. So dot is actually causing like, so it's called code vectorization. You can think of this as automatically added loop to actually go through each values of a vector or each value of an array and so on. There are, of course, again, some rules for this, but I'm cutting corners. I'm cutting corners before of time. So there is some example of pi approximation with rational numbers. But last but not least, Julia can be called, Julia can call many other programming languages, and more interesting, Python can be called natively from Julia, and you can load any Python library into your Julia installation. So this is maybe not interesting example, but I'm just loading here NumPy, okay? So you can use NumPy. Here it's a NumPy command, and running a NumPy command, I'm getting a Julia matrix. Okay, so it has two-way automatic integration of Python. Similarly, you can integrate with R and Fortran and C and many other programming languages. But basically, for example, HyperNetX has a great hypergraph visualization, and I'm working on a library named simplehypergraphs.gl that's using graphs. So I'm stealing some kind of visualization code. I'm just calling code by cliff in Python from Julia, okay, and it just works. So this is how can it be done. Okay, so this was about the language. Maybe it was too long, but now this will be about the graphs. Yes, it's supported automatically, namely the multiplication of operator. So if I have two matrices, okay, if I write 8 times b, this is a matrix, a multiplication from linear algebra. And if I want to multiple element by element, what do I need to do? Dot. Yeah, exactly. Good answer. I need to write a dot b. And then it's a vectorized multiplication operator. Okay, so it's very nice because it all feels like algebra. Okay, thank you very much for this question. Okay, so then we go to graphs. So we have, so in Julia we have a package named graphs. I'm also loading another package named graphplot. So just few sentences about the graph package. Okay, so GraphsGL is the library. The GraphsGL is a library for graphs processing. The one that we are going. Here is also another funny example. So I'm not going to run it, but I write it really about the power of Julia compilers. For example, it has a package calculus, and it can take any piece of Julia code and differentiate the code, and then calculate the derivative of the code. And you see it was sine, and here you have cosine. Okay, and then you can process this code, and you can attach such pieces of code into the compilation process. So this is really nice because you can symbolically process Julia code. The compiler can do very funny things in the compilation process, not in the runtime. And you compile the code only once for a few seconds, and then you run it for several hours if you are searching for some huge graph and its properties and so on. It takes long. Yep. Okay, this is great question. So let me just show you. If I have graphs, then I press dot and tab, and then you have the list. And of course, you can. So if I'm interested about something abstract graph, you can put question mark in front. And actually, it's also, this is maybe maybe too short explanation, but when we do a simple graph, it will be longer. So then you have then you type question simple graph, and then you have a full explanation and how to construct it, and then you have examples and so on. So it's question mark in front. Okay. So then we are going, so before building the graph, then what we have this graphs, graphs.gl library. So these are benchmarks from a few years ago, but basically the result and also newer benchmark, basically the speed of light graphs is similar to iGraph. It depends on the use case scenarios, and again you can find many benchmark, but this is as fast as any other best graph library you can find there. So it has comparable speed to libraries written in C. Or even better. So there are very nice implementations of several graph algorithms. It's written in pure Julia. It's in very funny way extensible. So one possible extension that was presented at the previous workshop, this was simple hypergraphs.gl. That, for example, when you have a hypergraph, a hypergraph in this library can be translated as a view of bijection. So you can represent hypergraph as a normal graph through a bijection. So for example, there are codes that in this library, simple hypergraphs, there are codes that automatically expose a hypergraph as a normal bijection. So just as a normal graph as a bijection, or as a two-section. And basically, you can also create your own graph providers. And there are libraries like, for example, for immutable graphs, because graphs.gl is supporting like adding and removing vertices. But if you decide that the graph is fully static, okay, that nothing changes, you never add a vertex, then you can slightly better optimize the code. So somebody wrote a library called immutable graphs, that you have graphs that nothing can be moved once you construct them, but then you have slightly better mathematical code, and so on, and it just works. Okay, so this is this library, and probably the rest makes sense only to present via source code. So as you can see, we are loading the packages by using, and the first thing we are going to do, so I'm creating here a graph, and the graph has 10 nodes. It's named G1, and then for I in 1 to 10, and I add an edge. Here we have greedy operator like in other languages. So if I minus 10, if I is lower than 10, then add I plus 1, otherwise add 1, because I want to create a circle of nodes. Okay, so this all nodes need to be in a circle. Okay, so this is the first thing to create the graph. Then you have layouts of the graph, and many of you know there are lots of graph embeddings, and actually so basic graph embeddings are available to this package, but there is also a dedicated package named network layouts that has really tons of different graph layouts on how you want to visualize the graph. Yeah, we just using it's the simplest one. It's also in network X and in other packages, Spring layout. Okay, so this is the layout. The layout is actually storing the information about location of points. So it's a tuple, so a pair of two vectors. Please note everything in Julia is typed. So if I have tuple, I need to have types for elements of a tuple. Then inside is a vector, and then I need a type for element for vector, because in order to efficiently compile the code, everything needs to be typed, and then sometimes those type information are quite long. Okay, so here we're plotting the graph, gplot, blah, and we provide the layout, and here is the plot. Another way to construct a graph is, okay, yes, you're right. I forgot to tell that because if I look at this layout object, okay, so it's a pair of two elements, of two vectors. So there are x coordinates and y coordinates, and now the gplot function takes 3 parameters or more, but 3 basic parameters are the graph, the coordinates of x coordinates of vertices, and y coordinates of vertices. So I want to do something which is variable unboxing, like similar to Python. Like in Python, it can also add box, 3 dots, and then it's going to do kind of a variable unboxing. So this tuple is being unboxed into 2 variables, into 2 function arguments. Okay, yeah, it's really. Okay, so it's because I'm doing everything as fast as I only can. So I'm going through too many things. Okay, so there's exclamation mark because there's a convention in the Julia language that whenever you mutate something, so whenever you're changing the argument, use exclamation marks in function names. But this is just a convention. Like for example, in some languages, or so here use underscore, like as a part of name. So this exclamation mark is only a part of name of the function. Okay, just to make it clear that it's mutating, because in Julia arguments are being passed by reference, more exactly passed by sharing, but whatever. So they are passed by reference, so the argument of a function can be mutated by function, contrary to say R, where everything gets copied each time. Yep.
Symbols for a name of a function.
It's surprisingly not limited. So you can basically whatever LaTeX symbol you can think of, or whatever Unicode symbol you can think of, then it could be, it could be name of function. So you could have zeta from beta, okay, and say this is square root of beta. So this is a valid. I didn't put the right beta. I put big beta. So this is a valid piece of Julia code. So basically everything what it's look like in your paper, it's a good name for Julia function. Okay, so this is the rule. Okay, so we have the layouts, we have printed the graphs. Then we can have an agency matrix. So you can also, of course, create. You can also create the graph. You can also create the graph using the agency matrix. So we are providing here the matrix, and then use the matrix as a constructor. So this time I'm plotting the matrix, and then I'm also using the labels for the edges. Yep.
What is G2 after G?
Okay, what is 2 after G? So I named this graph G2, and this you can use lower index. I can type G/_2. So whatever underscore. So most letters and symbols work for underscore. And then we have G2. Again, this is yet another example that it can look more like in your LaTeX paper than in a piece of code. So this naming. Okay, so we have the matrix named G2. Then we have agency. Then you can have an agency array. We have an agency array for this matrix, and there was a bigger one, G1, and you can see that the agency matrices are stored as something as sparse arrays. So Julia has an inbuilt support for sparse arrays because, of course, if you have, say, a graph like million by million edges, if you try then to make an agency matrix of that huge graph, it would end up bad because you do not have so much memory in your computer. And because in Julia we have sparse arrays for everything, actually lots of operations can be performed without materializing the data. I think even if I try to multiple, say, this matrix by 3, you can see it's still a sparse matrix. So lots of algebra informed operations on sparse arrays work in such a way that you have a sparse array in input and still sparse array as an output. So if you have a code that has, like, again, if you need to calculate something on agency matrices by million by million, lots of computations was going to work because you do not materialize the data. It knows it's sparse and it only, performs operations when there are no zero values. Okay, so so this is kind of useful. So the main function for plotting graphs is gplot. But also it's also quite easy to write your own code for plotting. So sometimes when I'm doing some custom plots, I have like 20 lines of Julia for my custom plotting. But the main function is gplot, and with gplot you have all of the standard options you might expect to plot the graph. So there is really tons of the options for formatting. Okay, so that's where you can plot it. Now we have a package. We have a package in Julia named colors, and then you can use something. This is called a text macro. So basically, this is being used. This is something you can put in front of text to give it another special meaning. So, for example, you have text macro named colorant that is for creating colors. So, if you want to create colors by name, but actually, like any programming language, if I'm going to show what is inside a color, is just a set of bits, red, green, blue, like every place else. So then if I have this colorant, of course, you can assign colors. So here I'm creating a graph of earth vertices and 12 edges at the random location. So this is a random graph of 8 vertices and 12 edges. And then I can, as you can see, I can use the gplot function. And of course, I can plot this graph. I can set the properties and so on. Now, these by default are, when I write graph, I'm getting an object with which undirected graph. In the graphs.gl, these are called simple graph. Okay, it's an undirected graph, but of course you can also create a directed graph. So I can say I want to have a random directed graph, 7 vertices, 10 edges. Okay, then I get such a graph. Now, we have several functions for generating graph. There is a function for all popular graphs. So all them, something maybe to be expected. All popular graphs are kind of implemented in the language. So for, say, in bull, house, karate, tute, help, and we have like bull graph, house graph, karate club, and tute graph. Okay, you have also for many specific graph constructs, we have also functions. So for example, suppose we want to have click a graph when we have 5 graphs, if a graph consisting of 5 joined graphs, each of 4 click, then we do click graph and then the graph is created. Popular algorithms are also implemented. So suppose we want to preferential attachment graph back, we do Parabasi-Albert, provide how big we want it, and then we have the Parabasi-Albert graph. Okay, so we have generated a preferential attachment graph. Pardon? No, it's not a tree because it's starting from many places, I would say. Or is it? No, yeah, it is a tree. Okay, yeah. Sorry. Okay. I think one is size, one is, okay, we would need to check because I forgot. Yeah, we do not have cycles. So, okay, so one is the size. Each new vertex with edges, blah blah blah. So these are the parameters of the graph.
K equal 1, I think. Yes. So K1 means 1 attached to 1.
Let me. It's if it's 3 arguments. This is the size of the initial graph. Then it's n0. Oh, okay, n0 is the size of initial graph. Yeah, we cannot start with 0 initial graph. Okay. Yeah, now it's not a tree. Yeah. Yes, so if you wanted to tree, this needs to be 1. Yeah, now it's okay. So this is the number of the edges. Okay, so then we have functions. Then we have functions for various graph properties, and before that we do weighted graphs. So the graphs also in this library can be weighted. So there is a separate library because there is some basic implementation of the graph, and there are many abstractions. So like weighted graph, and they all work together. So weighted graph is another abstraction when you can provide weight for the edges. And then we have add edge, and then we have add edge function. Now here we are using the dot operator to add many edges at once, okay? But we do not want to treat a graph as a vector because it would not make sense to treat a graph as a vector. So we vectorize over those parameters, but we do not vectorize over the graph itself. So ref here it's replacing the graph with a reference, but it's stopping the vectorization. So we have here. So we have here the indexes of vertices, first vertex, second vertex, and we have the weights for an example, and then we plot it. Okay, so this is a graph. Of course, when plotting, we can display labels over vertices, over edges. Then we have functions to iterate over graphs. So here we have some very simple graph, and then we have a function. Then we have functions, for example, to iterate over vertices. So if I type vertices the graph, I'm iterating over vertices. If I want edges, so each edge is actually an order pair from to where. So this is how it's being represented. Again, it's all typed, so it looks like a complex data structure, but underneath there are just 16 bits or 16 bytes or two numbers. Okay, so it's all. So sometimes those Julia data structures look complex, but again, underlying there are just numbers, and that can lead to efficiently compiled code because everything is typed. So here, for example, if I go to edges, if for each edge I want to recover source and destination, then we have the function source and destination of the edge. And here is something which is called text interpolation. So if I take a piece of text, then I can put here the first element and second element, and this is how it's going to play. So the first edge was from 1 to 1, the second from 1 to 3, and so on. Agency matrix has been discussed. We can have also incidence matrix. Then we have manipulating graph. So when we have a graph we can add vertices and edges. So here I'm creating an empty graph, adding an edge, adding an edge. So here I added 5 vertices in one comment. So I've added 5 vertices, and then to all those vertices I can add corresponding edges. Then again I have I have this simple graph. Then of course I have a graph. Then I can add additional edges and so on. So one of applications, Julia, when it's quite useful, is running numerical simulations on graph. So here you have a sample model, a sample simulation model of pandemic. So I assume this all, I've been creating the slides during COVID or so it's always pandemic everywhere. So I'm loading here the libraries. I will be creating small word network graph using the Strogatz algorithm. And suppose I have some, so here I'm using data structure. So this is an example of some data structures over the graph. So I have here a person, they might be infected with some type of the virus. They are getting infected at some step. Then I can define something, which is a simulation model. So I have some population, and population is a group of people. So this is a vector of persons. Then I have the graph. That is simulation. I have the layout, so it's not changing every time I'm generating the visualization, and I have the number of steps. Also, it's mutable. Mutable means that object can change state. If you create a data structure in Julia, you can define whether it's mutable or immutable, and then it's differently stored in the memory, and it affects the efficiency. Okay, so here we have some small simulation model with a single person infected at the beginning. So here I can show what is inside the population. And then here we have very simple function for plotting, and we have 2 types of diseases. So green people are healthy, blue people are sick by the blue disease, and red people are sick by the red disease. And then we can, or this could be like information widespread in a network or similar. And having this type of data, then we can run the simulation model. So here we have a simple function where 2 people are interacting, and then in each step we are selecting a random person. We are selecting the other person that they are interacting with, and if the disease is conveyed, then it's like any model. This is just sample code. Pardon? No, in this model not, but of course it's easy to extend. So it's just simple model. Okay, and then for example, for some sample simulation that I have run, I have number of people being infected by the disease A and the number of people being infected by the disease 2. And I can of course adjust size of the plot. I think I have slightly too small with this number of agents, those points. But then you can see, for example, at some stage of simulation, I have some population of red and blue. But this is just an example of how simulation model is going to look like. I didn't want to get into details, but just show you that basically the codes are not very huge and they are more or less readable, and it's not so difficult. It's not so difficult to write any numerical simulations in the language. So this is like, like a tutorial. And this has also been uploaded to this address. So, if you want to experiment with something more useful, then it's okay. So thank you very much for your attention. I think I'm more or less in time. So now I understand that we have a lunch break, so it's hard to compete with. So thank you very much.